fermion, then it's anti-fermion. Okay, so this is very good. Now let us get back to quantum mechanics and let us complete the missing things there that we have left. For giving you an analogy, the whole theme actually, I was impressed with this particular thing, and I thought originally I had not thought of telling these things. I was about to start on the actions of relativistic point particles, then Polyakov action and Namugoto action and so on for particle and for field theory, D0 grain and D1 grain. But I thought this is a very important question, and we should first know, I mean, what are we going to do in the rest of the lectures? We want to generate all this physics. We want to understand all this physics. That is the outcome of. So here, like C dagger on operating on zero vacuum, giving you one electron state, or D dagger operating on vacuum, giving you one positron state. This is just a symbolic that I am trying to explain to you. Then similarly, in string theory and superstring theory, we would have some corresponding. In string theory, they are usually called as modes, but they are actually annihilation and creation operators. They call them as modes. The string people call them as modes. So for bosonic string theory, they would be bosonic in nature. For superstring theory would contain both bosonic plus fermionic. So fermionic would be analogous to this Dirac theory. Okay. In fact, this is what I have just now written it for the 4-dimensional Dirac theory. But in string theory, you actually do field theory in 2 dimensions. In string theory, your x mu are the coordinates, string coordinates, or the fields which are analogous to phi. And they are real. So there is no phi star. So there is no x mu star. X mu star is equal to x mu. X mu is real. And similarly, in fermionic, when we introduce Fermi fields into our string theory, in our superstring theory, we ask them to be Majorana spinors. You see, nature is also helping us. So Majorana spinors have real components. So psi mu star would be psi mu. Okay. So that would be an advantage to deal with those things. And what else? So, but essentially here they are functions of 4. All these phi, phi star, psi, psi star, they are functions of x, y, z and t. But in string theory, they are functions of only 2 of them. Let us say t and x, which we would call as sigma and tau in string theory, and not 4. So that is only a 2-dimensional field theory. What happens is that is a 2-dimensional theory on the worldsheet. In the case of superstring, on the super worldsheet, but the x mu or psi mu, they are, x mu is a mu vector in the space-time, or the target space-time, or the background space-time, right? And psi mu is a spinor mu in space-time, but a spinor on the worldsheet and a mu vector on the space-time. You should catch my slips that I make. Thank you very much. She was able to catch my slip that last time I had slipped T duality with S duality. For T I would have said, for T duality it is a compactification on a circle of radius r and compactification on a circle of radius alpha prime by r. They are equivalent, right? And I had mismatched the, I called it S, and that S I called as T, where strong and weak coupling. So you should keep correcting me. I would be happy with that. Okay. Let me now these are some important points which we need to recap in the context of the harmonic oscillator. So I come back to 1-dimensional harmonic oscillator and I say that, and let me collect important results here, and this is by definition, we define it, okay? We define it like that, and then you can prove n of A, which is A dagger A and you can find it out. This would be minus A, and n of A dagger, this would be A dagger A dagger, and this would be plus of A dagger. We will have to carefully check and catch how would these things change when I consider a fermionic oscillator instead of a bosonic oscillator. Alright? So this is all bosonic, and here you can prove that n A dagger n H n A dagger plus A dagger n, this on n, this would be n A dagger is plus A dagger plus A dagger plus A dagger n times n, this would be n plus 1 A dagger n, n plus 1 A dagger n, yes. So, and in the first step, I should change it to A dagger plus A dagger. This would give me little n here times n, and this would give me A n plus 1 A dagger n. Okay, so that is why I said that if I postulate or if I define this n to be an eigenstate of this operator n with eigenvalue little n, then automatically I obtain that A dagger n is the eigenstate of n with the eigenvalue increased by 1. So increase of the eigenvalue of 1 actually what it means is the increase in the quantum unit of energy h cross omega in the system. So similarly you can prove that n on the same logic you can prove that this is n minus 1. So here the eigenvalue is decreased by 1. And obviously this, if you once again allow me to write this is A dagger A, and this is n, so it preserves the eigenvalue at its original value. That is the idea. So these are three important points. One more important point about this is we are always mentioning this little n. So let me consider the norm of a state. Norm of a state an. So as we know, in Hilbert space, all states are supposed to have positive definite norm, okay, and positive definite expectation values. So if I want to calculate the norm of state an, this should also come out to positive. Every state should have a positive norm. So what is the norm of this? Norm of this is equal to an dagger an psi dagger psi, and this should be, this comes here and this becomes A dagger. So it is this times A times n, and this H equals to n, and this gives me n, and this gives me n, this gives me m delta and n. This is equal to n. Right? So if I would be considering field theory for this, so that I would also have this dependence on k dependence, then here I would have n of k. Okay? And this is we have calculated the norm of a state. So this has to be positive definite. So this is greater than 0. So what we arrive at the relation that by requiring that an has a positive norm, we arrive at nk is greater than 0 or 1. Then only can the norm be positive definite, otherwise the norm will not be positive definite. So, but this has a very big physical meaning. And what is that physical meaning here? That n is of course an integer, so 0, 1, 2, 3. There is no upper limit on nk. This means any number of particles with the same momentum could stay in the same quantum state. Many particles could stay in the same quantum state. So that means this is, without being told, we are talking about Bose-Einstein statistics or just Bose statistics or bosons. And we are not surprised, because in our entire theory we have never introduced fermions so far. It's only X and P, they were bosonic, A and A dagger, they were bosonic, everything was bosonic. And they were primarily based on the commutation relations of X and P, which were bosonic, and not on anti-commutation relations. Okay? In any case, we don't even have anti-commutation relations for X and P. We have commutation relations for X and P. So, here, this, what you obtain, that nk, so actually, although I am just proving it for quantum mechanics, one-dimensional harmonic oscillator, but the same thing you have to write, you just also put these, for all these things like n, you write it like this. You write the momentum dependence also, and also for this state nk, so then this is nk times nk, and then you are doing field theory. So here we are, that's why I am considering these three cases parallel to each other: quantum mechanics, one-dimensional harmonic oscillator, real scalar field theory, and complex scalar field theory. Why you sometimes need complex scalar field theory, but otherwise in real scalar field theory the charge operator would come out to be 0. Okay, other things will come out fine. And as long as you do quantum mechanics, you only obtain conservation of energy and momentum. But you also do field theory, then so maybe at the moment I can remove this side from here. So all what holds here, but symbolically when you, algebraically when you write some of these expressions, in particular in field theory, then they need to have explicit dependence on the momentum. Okay, that's the only thing. And here nk, in the very beginning I had given the definition of this nk. So let me, after writing this, let me now redefine it again. So this is n of k1, n of k2, n of ki. So this is a particle state nki. It is written like this. So and number of particles with momentum k1 and number of particles with momentum k2 and so on. Okay, and this is the so, and what is this thing? Now this so what it means when we say that a system, a quantum mechanical system or a quantum field theory system is in a state n. What it means? It means that the system in the state n, I could put a system in the state n is an assembly of capital N non-interacting particles, each of energy h cross omega q. And when you operate on this with a creation operator, this increases by 1 quantum unit of h cross omega. Then you operate on this with a operator A, the annihilation operator. The quantum unit of energy of the system goes down by 1 quantum unit of h cross omega. Okay, that's the idea. So, and that is why. So actually, that actually justifies the name why you call them creation and annihilation operators. Annihilation operators are also called as absorption operators. Okay, some people call them ladder operators. So there are many technical. But they mean the same. I personally am more used to calling them annihilation and creation operators. It annihilates the state and it decreases the eigenvalue by 1. So you see, once you develop something for one-dimensional harmonic oscillator, for example, in quantum mechanics, it's just straightforward to apply to develop it for the field theory. And let me have a look at my parts. We have time, so should I give you an let me give little more on, let me work little more on this, okay, before we don't have to, when I aim at finishing something, I become faster. And I remember Sarah had once advised me last summer that I should try to be little bit slow if possible, if I'm too fast. And for this I discovered, when is this possible? If I do not aim at finishing all these things in one lecture, then I remain slow. If I aim at, okay, I have to go all the way up to that, then I tend to become faster, which is not good. Okay, for the audience, that's not good. So let me complete a few more important results on this. Actually, I'm trying to understand the bosonic oscillator or the simple harmonic oscillator. It is most important, it is most crucial. If you look at all string theory books and review articles, they in between, when they come to this particle interpretation of the theory, they come back to one-dimensional harmonic oscillator. Because otherwise you cannot explain things what you are talking about. Okay, so it's easier to talk about them with this. And two more important results. A dagger on N, I'm writing in quantum mechanics language, N plus 1, N plus 1, and A, N, n minus 1. So I can invert this thing again and I can write n plus 1 as 1 divided by square root of n plus 1 times a dagger n. And from here let us see if we from here, if I say A, if I put n equal to 0 here, then I get this is 0. So this gives me the definition of a vacuum state. So that A operating on the ground state n equal to 0 gives me 0. So that actually you get the definition of the vacuum state. You cannot kill the same word twice, as the quotation goes, although we shouldn't kill it even once, but as the proverb says, so if it's already ground state, you can't kill it further. Okay, so you get a 0. But now let us try to put n equal to, if you put n equal to 0 here, then you have one particle state, then this is 1, this is 0, so this is 1, and so it's other way around. So you apply your creation operator to the ground state and you get one particle state, right? So in field theory, I would write it this also, A of K operating on 0 gives me 0. Here I would write it as a dagger of K prime operating on this, or sometimes even you can write it K. So this is one particle state. If you want to have a two particle state, so you apply with another A dagger of K prime, A dagger of K, no, once K prime, and you apply it on 0, you would have one particle state of K and one particle of state with K prime, and so this is the two particle state. Okay, that's a two particle state, but these two particles have different momentum levels here, K and K prime. Okay, and just to mention, whenever I would have fermionic oscillators, I would not be able to put two identical ones into the shape. We will see when we consider. I am not sure if we do it today, but we will do it. Because hurriedly I shouldn't do anything which goes above the head, it's no point, right? So, okay. So this is, and similarly you can have operated once again with A dagger, you get a three particle state. And this we always have to remember, where did we get these A and A daggers from? What was the original theory? Okay, that would tell us. So our whole purpose is to try to understand what is there in this one particle, two particle, three particle, n particles. What kind of particles are they? That would be determined by the nature of these, and this would be determined by the Fock space decomposition that we used for our field, or for our X or P, or for our phi and phi dagger or phi dot. So, but it is usually, it's enough that you define the Fock space decomposition for phi, because phi you can always calculate the momentum, maybe in terms of the time derivative of phi. So you automatically also know the Fock space decomposition for pi, right? And but if you have two kinds of particles in the theory, like in the complex scalar field theory, so A and B type of particles, or if you have a Dirac spinor theory, then you have particles like fermion and anti-fermion, or electron and positron. So you have C and D dagger. Then when you write its direct adjoint of psi, you write D and C dagger. So C and C dagger, they annihilate or create one kind of particle, let it be an electron. Then D and D dagger would annihilate or create its antifermion, which is going to be a positron. So we have to always link it from there, and the same logic we would use in string theory, but because we would use them repeatedly at many places in different ways, so I think things would be very, very clear. And here let us go a little bit further. So this now I can remove the definition of this, and here if you apply it repeatedly, you can find that n, this is a dagger to the power n divided by factorial n, square root of that, times this. And what it means in field theory, so it's here, I have it on the very first page. So in QFT, I would write AKI operating on N of K1, N of K2, N of Ki. This should give me this one, square root of n. So n of Ki square root of that times this same state n of K1, n of K2, but this is n minus 1 here, okay? So this is nki minus 1. You see? But this operator AKI is doing here, it would decrease this nki by 1. It would decrease this value by 1 and leave all others the same. And the other expression for a dagger of Ki operating on n of Ki. Now this would give me, now this one is to be used. Now this one is to be used. So square root of nki plus 1 and square root of that times nk1 nki plus 1. Is this okay? Yeah? It's the same thing that I have written here. A dagger n is square root of n plus 1, n plus 1. A dagger ki, so this would increase this nk of I by 1. So if I am writing it for real scalar field theory or complex scalar field theory, this is how I would write it. Okay? But it's much easier for me to remember it. So I usually remember things in quantum mechanics, and by analogy you can always write it for field theory. And this one, the last one. So this would be nk1, nk2, etc. nki plus 1, this, which is analogous to this, is now equal to 1 by square root of this. So product of the nk1 factorial nk2 factorial nki factorial dot dot dot, all these continue, and this 1 by this raised to the power 1/2 times a dagger of k1 raised to the power n of k1, a dagger of k2 raised to the power n of k2, and so on, times so what is this ground state? This ground state, which is denoted by this, is 0, 0, 0. 0 number of particles with momentum k1, 0 number of particles with momentum k2, and so on. So there are no particles. So this is how you would write the vacuum state in the field theory. And I think we should perhaps stop here. My watch says 1:51, so otherwise we would miss our lunch, and we continue our story next time. So next time I would take off from here without maybe recapping anything from today. We can proceed further to complete the, and then we can consider fermionic oscillator and try to see what happens there. This is more important, going to be more important for superstrings, because we will introduce Fermi fields into our theory. Okay. So Sarah, I'm sorry I have not been able to answer your question fully in one lecture. I need to continue to be able to answer it further. But believe me, many, I think hundreds and thousands of giant, great physicists have worked on these things for decades to develop all these things. And it's nice to try to understand what it means. And fortunately for us, we are born in a very fortunate time that now we already happen to know many of these things. We have not to struggle for creating them. We only have to know them. And then we can apply them further. Okay? So we proceed further, and I continue answering your question next time. And thank you all very, very much. Thank you all very, very much for hearing me.